Hi everyone, my name is Ziwei Wang. I'm a PhD student at Australian National University. Today in this video, I want to introduce you to our recent research on stereo hybrid event frame cameras for 3D perception. First, someone might ask, what is an event camera? The event camera outputs asynchronous intensity changes of each pixel in continuous time, which is different from the frame-based cameras that image absolute intensity for all pixels at a certain frequency. If you look at this figure, the z-axis is time. The absolute intensity of the moving shapes is captured by frames at a certain frequency. Frame cameras are blind between consecutive frames, but the blue and red events are triggered continuously between frames and only occur around the moving shapes. That's because event cameras have microsecond time resolution and only generate events at pixels with intensity changes, so event cameras provide temporally dense and spatially sparse event data. That also means it is hard for event cameras to capture static scenes like frame cameras. But the frame-based cameras suffer from low dynamic range. You can also see the two pictures with a dog and a window. If we open the exposure time long enough, we can see the dog in the dark clearly. But the bright view outside the window is overexposed. Also, if you open the exposure for too long, or if you want to capture fast motions, frames start to suffer from blur because objects might move across a few pixels during the frame exposure time. But event cameras provide data with a high dynamic range, around 120 dB, compared to the 60 dB of the frame-based camera. And event cameras almost have no image blur. As you can see, these characters of event and frame sensors, they are very complementary. It motivates us to build a hybrid event frame sensor system and fuse this data. If we fuse event and frame data, what can we get? We should be able to get images that are spatially and temporally dense. That means if we want to know what happens between frames, full images are available at any timestamp. And we should be able to get images with high dynamic range in absolute intensity scale and be able to image both static scenes and highly dynamic scenes without blur. Currently, Davis camera is the most popular hybrid event frame camera that shares the same photodiode and provides registered event data and frames at pixel level. But the inbuilt hybrid configuration also limits the quality of both event and frame data. Currently, the highest quality of the hybrid event frame camera has a much lower resolution than the pure event cameras. And the pure event sensors are developing faster than the hybrid event frame sensors. That's why we want to study the stereo hybrid event frame system. The stereo configuration allows us to simply integrate event sensors into existing sensor suites, like the multi-camera system you can find on mobile phones and robotic systems. To register event data with existing systems, it is necessary to estimate the disparity between the separate sensors. To study this topic, we built our SHEF camera system and introduced the first dataset targeted specifically at stereo hybrid event frame data for near-field scenes, and we also provide a baseline algorithm to compute disparity. Our SHEF camera system includes a separate event camera and a frame camera alongside each other. We synchronize the two cameras by sending a trigger signal from the frame camera to the event camera. We mount the system rigidly on the UFI robot manipulator to guide the controlled motion and accurate camera pose. The camera motion is controlled by the UFI robot manipulator. It follows 5 predefined trajectories at 3 speeds. The extrinsic parameters of both cameras with respect to the robot arm are also calibrated, so we can compute the accurate camera pose from the UR5 kinematics model. We have collected data set in 3 environments with a depth range from 1.5 to 4.5 meters. This is the way we collect data sets. We record frames and events at the same time. The UR5 trajectory is smooth, and we also design 3 types of Lissajous curves for the camera motion. Here are the 3 physical environments. We built a dense point cloud and a 3D reconstruction model for each setup with a commercial software 3DF cipher. For each frame, we can compute depth ground truth from the 3D point and camera extrinsic. The problem we propose is still very open. We also provide the first cut algorithm, or you can call it a baseline algorithm for disparity. It's a simple but effective method. I can go through it very quickly. At this stage, we only compute disparity at each frame timestamp. For the frame data, we compute an edge map using a classical Sobel filter, and then apply a threshold to generate the corresponding binary edge map. For event data, we first use a high-pass filter to reconstruct an intensity image from events. It only picks up information at edges. So similarly, we apply a threshold method to the image to get a binary map. Now we have the left edge image from frame data and the right image from the high-pass event data, and we do a standard image matching using cross-correlation with a sliding window along the epipolar line. In the next step, we use a classical close-to-fine framework with a 5-level pyramid to get more accurate disparity. The algorithm is very simple, but we actually get very good results, even though there are some filling points and we lost some information here. It is because the edge maps from event data are still very noisy at some edges, but apart from that, as a baseline algorithm, it has achieved very good results. We estimate the disparity estimation quality using 3 metrics: the root mean square error, the BAP, and the in-layer ratios. The BAP is a standard metric of KITI, which computes the percentage of byte pixels averaged over pixels with disparity estimate. The in-layer ratios measure the percentage of the disparity error within the preset maximum value. As you can see, our algorithm performs well in all 3 metrics. To demonstrate the potential of our system and for better visualization, we can also use a basic sparse-to-dense disparity completion network to combine a sparse disparity map and a dense image to generate a dense disparity map. That's basically everything for this paper. In summary, we discuss the advantages of the hybrid event frame sensors and the stereo camera configuration. We introduce the high-quality dataset for 3D perception, and we also provide a baseline disparity estimation algorithm for event and frame data. Thank you for listening. Thanks.